All right, here is day 39, part 2. So a random variable, this is chapter 16. A random variable is a numerical variable whose value depends on the outcome of a chance experiment. X could be the number of heads in 3 flips of a coin. So then we'd have to look at all kinds of things. X is the length of a pencil. Okay, and these are two very distinctly different types of distributions. This one here is called a discrete. The top one is called a discrete random variable if the set of possible values is a collection of isolated points. So when you flip a coin 3 times, there are exactly the number of heads could be 0, 1, 2, or 3. That's how many heads you could get. You can't get 2.5 if you flip a coin 3 times. A discrete random variable is one where you can get distinct values, okay? A random variable is continuous if the set of possible values include an entire interval on a number line. That would be the length of a pencil. If you sharpen a pencil, do you know, I mean, you might know what it started with, but you sharpen it, you don't just stop at exact values. So basically you cannot list all lengths of a pencil. So since you can't do that, this is a continuous random variable. All right, so a couple of examples: shoe size versus foot length. Okay, shoe size is something that is definite. Shoe size is discrete because I can list shoe sizes. Okay, there's a list of them at the shoe store. They have shoe sizes. You can go back and find them in a box. But foot length, you know, you might wear a size 9, but not everybody who wears a size 9 has the same foot length. This is continuous. Okay, age versus number of birthdays. Your age is continuous. Okay, you age continuously every day, but the number of birthdays is discrete because you can list the number of birthdays you've had. So a probability distribution now, for the rest of the year we're going to deal with these and normal models. So a probability distribution or probability model of a discrete random variable, X, lists the possible values of X and their probabilities. This is usually done in a table, probability histogram or formula. So we're going to do lots of tables. So we're going to let X equal the number of heads in 2 flips of a coin. So then the probability distribution of X is, so we're going to first look at a table. We're going to make a table for this. So first of all, we have to look at what are the different things that could happen. Okay, what are the outcomes? Okay, what are the outcomes? So basically I'm going to flip the coin twice, so I could get heads, heads. I could get heads first, tails second. I could get tails then heads, and I could get 2 tails. So there's my outcomes. There are 4 outcomes, okay? So now X is the number of heads. So my table is going to be, all right, across the top X is going to be the number of heads. So number of heads. So what are the number of heads that I can get? I could get no heads, 1 or 2. That's it. That's all I can get. Okay, so now here is the probability that X equals X. So the probability that X is 0. Out of these 4 outcomes, how many had no heads? That would be 1 out of 4. Out of these outcomes, the probability that X equals 1. So this is the probability that X equals 0. No heads. No heads. That was one of these, this one right here. What's the probability that X equals 1 now? Well, 1 head, those 2 options, so 2 out of 4, or 1/2 of the options. The probability is 1/2. And then the probability that X equals 2, well, 2 heads, that would be 1 out of 4. All right, so this is our probability distribution. The probabilities should all add up to 1, so 1/4 plus 1/2 plus 1/4 is 1. So this is correct. So now what does our histogram look like? So a histogram, let's see, what falls in 0, 1, and 2? This is the number of heads. So that would, well, the probability distribution of x is, I don't know if this is the best way to do this graph here, so we'll skip the histogram for now. So the probabilities in a distribution give information about the long run behavior of the variable. That is, probabilities are predicted, relative frequencies. And we talked about this earlier when we talked about at the beginning of chapter 11, 14, and 15 that a probability is based on repeatedly doing something over and over. So for example, if the probability that x equals 2 is 0.25, then after many observations of x, the value x equals 2 will occur 25% of the time on average. So the mean of a random variable x, denoted mu with a little x below it, describes where the probability distribution of x is centered. Okay? It's also known as E of x or mu of x. That is the mean of a random variable. And we are going to calculate that on the next page. So we're going to be finding the mean of this distribution right here.
Snapchat listening to this.
So we're going to let x equal the number of license plates on a randomly selected car. The probability distribution of x is shown in the table below. So we want to find the mean of the value of x. So in order to find the mean, E of x or mu of x, this is the mean of a random variable. Okay, so to find the mean of a random variable, what we're going to do to find mu of x is we're going to take every x value times its probability. And we're going to add those up. So we're going to take every x value times its probability, we're going to add those up, and then we're going to divide. Well, basically, that's all we're going to do. So every x value times its probability and then add them up. So to do that, I'm going to take 0.05 times 0 plus 0.25 times 1 plus 0.7 times 2. So every x value, 0 times its probability. I'm basically just multiplying up and down and then adding all those together. So when you do that, 0.05 times 0 plus 0.25 times 1 plus 0.7 times 2 is 1.65. So 1.65 would be the expected value. It's called the expected value, or the mean of a random variable. Or that would be mu of x. So the expected value, E of x, 1.65, it's also known as mu of x, the mean of a random variable. So we've got the formula down here, the mean of a discrete random variable. That's where we can name the values with single numbers. It's not continuous. We multiply each x value times its probability and add them all together. The term expected value, E of x, is sometimes used in place of the mean, mu of x. So the expected mean will not necessarily be equal to one of the values in the distribution. Instead, we interpret the expected value as long-term average. So for example, if we were to select many cars, you would expect there to be 1.65 license plates per car on average. So this goes with the law of large numbers. You just do things repeatedly, you're going to end up with that correct percentage or probability. So now we're going to play a game here, and I suppose I ask you to play a betting game with me. You bet $5, and if you draw an ace of hearts, I will pay you $100. If you get any other ace, I will pay you $10, and if you get any other heart, I'll give you your money back. If you get any other card, keep your money. So here's what we're going to create: a probability model for the amount I can win. So X is the amount I can win. And it really doesn't matter how you look at your winnings, but we're going to just go by, make it easy. So X, what are the different amounts that I can win? So the different amounts that I can win, I could win $0. Okay, so $0. I bet 5 and I don't win anything. So the other amount I can win is $5. I can also win $10 and I can win $100. So now I need to find the probability of each of those. So now this is going to deal with the number of cards in the deck. So let's see, let's talk about the $100. So if I get an ace of hearts, I'm going to get $100. So that would be 1 out of 52 cards are an ace of hearts. If you get any other ace, okay, $10. So you win $10 for the 3 out of 52. And if you get any other heart, your money back. So there's 13 hearts. 1 is the ace of hearts here, so this will be 12 out of 52 will be the probability. And then $0 if you get any other card, so that's 15, 16 cards, so that we've already used up, so 52 minus 16 cards. So there are 36 out of 52 ways that we're not going to win any money. So there's our probability model. And now we would like to answer the question, should I play this game? To answer the question, should I play this game, we would like to find the mean or expected value. How much do you expect to win? How much do you expect to win should you play? So the mean of x, mu of x, we take every x value times its probability and add them up. So every x value, that should be 5, times its probability, 12 out of 52, plus the x value of 10 times its probability, 3 out of 52, plus 100 times 1 out of 52, and we just add those up. And if you do that on your calculator, you get that you can expect to win on average $3.65 in the long run if you play a lot. So should you play this game? If you have to put $5 down, in the long run you're only going to win $3.65, I would say no, don't play. It's a waste of money. Alright, so now the standard deviation here. The standard deviation, so we can now find the standard deviation. How far away are they from the center on average? So this, of course, is the standard deviation. So using the license plate distribution from earlier, if we had a sample of 100 cars, we would expect 5 zeros, 25 ones, 72s. And so here's the basic calculation that they did. We take each value minus the expected value squared, okay? It's easiest if we just go down here and look at the notes in the actual formula. So on average, the number of license plates on a car will be 0.57 from the mean value of 165. So note we divide by n instead of n minus 1 and use the symbol sigma sub x instead of s sub x. So this is the standard deviation, sigma sub x. Since we're not calculating the value of a sample, there's no uncertainty about values in the distribution. We made the probability distribution. So it's calculated a lot the same way the standard deviation of a data set, except that we weight each value with its probability, since the values that show up more often should have more influence. So here is the actual formula that you're going to use. So the standard deviation of a discrete random variable is the square root of the sum of the difference between every x value minus its mean, the expected value squared, times the probability. So you calculate that difference, square it, take it times the probability, and then add them all up. So the variance of a discrete random variable is just the standard deviation squared. So we would like to find and interpret the standard deviation for the betting game from earlier. So sigma, we already have equals the square root of the expected value, e of x, mu sub x was 3.65. So we take every x value. The x values were 0, 5, 10, and 100. And we take each of those, so 0 minus 3.65 squared times its probability.